This is called the extreme value theorem. And it's sort of cool because it's useful in actual applications. So here it is. Suppose that I have a function that's continuous on this closed interval from a to b. Then f of x will attain an absolute maximum at some point and an absolute minimum at some other point for some values x equals c and x equals d inside of that region. Okay? So this is actually a really important theorem. If we have a continuous function and you're going to truncate, then somewhere in there it's going to be the highest, and somewhere in there it's going to be the lowest. And we can actually find that. Let's take a look at a little example of this visually, sort of see this theorem in action. Actually, you know what? I want this theorem here because I don't want you to forget it. So how about y equals sine of x, but let's now truncate the world from 0 to 3 pi. So only look at the function from here to here. I'm looking for max and mins. Well, we can look at this visually and see, yes, there are going to be two summits, two max, right? And so the maximum value is going to be 1, and it's going to occur here at pi over 2, and here at 2 pi plus pi over 2. And what about the minimum values? Well, there's this minimum value here at -1, which happens here at pi plus pi over 2. And that minimum value is -1. But there are two local minima as well. Do you see them? Those are the endpoints right here at x equals 0 and x equals 3 pi. Those are always max mins. In this case, they're both mins, and you can see that. So the absolute, though, absolute maximum value is 1. The absolute minimum value is -1. So you can see an example of that. Now, this theorem looks kind of complicated, right? There's lots of words here. Are all the words necessary? For example, do we really have to have the function be continuous? Do we really have to have it on a closed interval, which means we include the endpoints? Well, the answer is yes to both of those. Let me show you some counterexamples. So suppose that we remove continuity. Let me show you an example that's not continuous on a closed interval and does not attain either a max or a min. The function I'm going to look at is f of x equals 1 over x when I'm between 0 and 1, not including 0, or between -1 and 0, not including 0. And let me just define the function to be 0 when x equals 0. So here's the graph. It's actually kind of like the standard hyperbola, but I've threw in the point at 0 and made it 0, and I've truncated the world at 1 and -1. So it's actually a hyperbola that's been cut, and we've added this extra point. All right. Well, it's defined everywhere. Between -1 and 1, this function is defined. Think of any number at all, and in fact, I can plug it into this. Even 0, because I'm defining it to be 0 there. Okay, but does this attain a maximum value? Well, let's see. No, because this wing is getting higher and higher and higher without bound. It's heading toward infinity. The function is defined to be 0 way over here, but no matter where you pick a point, I can actually get higher. Similarly, down here, this is getting lower and lower and lower without any kind of bound, so there's no minimum. So you need continuity. This function is not continuous at 0, because you can see there's this dramatic break. The limit doesn't even exist there. Okay, what about if we have the function continuous on the open interval? For example, y equals 1 over x squared minus 1 on the open interval from -1 to 1. That means that it's continuous everywhere inside, but not necessarily at those points. And in fact, you can see that when you plug in 1 or -1, this function is undefined. It's 1 over 0, which is undefined. So it's nice and continuous here. But what about the maximum? Well, this one actually has an absolute maximum value. You can see it. That actual value is going to be when x equals 0, and the value itself is -1. But what about an absolute min? Well, no, because no matter where you think you're the lowest, this thing goes down forever and goes past it. So this has no absolute min, and that's why you need the function to be continuous and defined on the entire closed interval. You know, in math terms, this actual phrase, this closed interval, is called a compact interval, because it's compact, and that's what you need here, and that's the idea. All right, great. Let's take a look at an example where, in fact, it's difficult to sort of see it, but we can still do the math. How about f of x equals e to the x sine of x on the interval from 0 to 3. All right, so let's actually do this one live. How are we going to do it? Well, I've got to find the critical points. So I've got to compute a derivative. So here we go. F prime of x. Well, this is a product of two functions, so I have to use the product rule. So the first times the derivative of the second plus the second times the derivative of the first. So I have the first times the derivative of the second. And what's the derivative of sine? Well, that's cosine. Plus the second, which is sine, times the derivative of the first. And the derivative of e to the x is e to the x. So to find the critical points, I want to find the points where this doesn't exist and where this equals 0. Well, e to the x is defined everywhere. Cosine is defined everywhere. Sine is defined everywhere. So in fact, this exists everywhere. So the only candidates we're going to have for critical points are when we set this equal to 0. So I have to factor out the e to the x. That's a common factor. I have cosine x plus sine x equals 0. E to the x is never 0, so I can actually divide both sides by e to the x. It's never 0. So that makes life a lot easier. Look how easy this is. This is great. So I have cosine of x plus sine of x equals 0, which means I want to solve cosine x equals negative sine of x. So now what are the solutions to that? Well, let's just do it really fast by looking at a picture. So let's just graph this really quickly. So the cosine function, how does that go? It starts way up here, goes down, comes up. That's 2 pi right here. Now, I'm only looking between 0 and 3. 3 is just a little bit under pi. Now, here's pi, so I'm looking a little bit to the left of that point here, so I don't even care about that. Now, where's negative sine? Well, first of all, let me just draw in sine, because that's an easy thing to draw in. So sine looks like this. Just doing this lightly, so it's to remind us where sine is. So there's sine, and so negative sine is the flip of that. So here we go as the flip. So that's negative sine of x, and this is the cosine function. And so I'm looking for when they're equal. Well, they're equal right here. And where is that? Well, if you think about it, that's kind of the same point as here, but shifted over a little bit. This point of intersection, we know, that's pi over 4. We know that sine and cosine agree at pi over 4. And so if I take pi and I move over pi over 4 this way, what am I left with? I'm left with 3 pi over 4. So without doing any work at all, I see on this interval right here, the only solution we have, the candidate we have, is 3 pi over 4. So that's one critical point. But remember, endpoints are always extrema. So we better check out what's happening at 0 and what's happening at 3. So let's do that right now and see what's happening. So when I plug in 0 into this function, what do I see? I see e to the 0 times sine of 0. Well, e to the 0 is 1, sine of 0 is 0, so I get 0. Okay, that's the value there. And then what is f of 3? Well, f of 3 is going to be e cubed sine of 3. All right, I don't know that off the top of my head, so I got to use a calculator or something. And I see it's around 2.83. And finally, I got to plug in this critical value, which is 3 pi over 4. And what do I get? I get e to the 3 pi over 4 times sine of 3 pi over 4. And again, here, I don't know e to the 3 pi over 4, so I got to approximate this, and I get 7.46 something. So I'm looking for the rock bottom lowest, the rock bottom biggest. It's easy to see this is the biggest. So we've got the absolute max happening at 3 pi over 4, and the absolute value of that max is 7.46. And the drop dead min is happening at x equals 0, and it's 0. Is this really the case? Let's take a look at a picture and see if we can reveal the mystery. From 0 to 3, here is the curve, and you can see it's exactly what we predicted. That lowest point here is at 0. This point, at endpoint, is a min, but it's just a local min. And the max is way up here at around where we estimated it to be. So, in fact, you can extend this principle, this idea. And here's how you find, in fact, the absolute max and min on a closed interval when you're dealing with a continuous function. First of all, you've got to find the critical points, places where the derivative is 0 or the derivative doesn't exist, and then evaluate the function there to see those actual heights. Then what you want to do is evaluate the function at the endpoints. So a and b are the endpoints here. So We find out where the derivative is 0, doesn't exist. We plug back into the original function and find out their heights. Then we take a look at the endpoint values. And the largest value along that list is the absolute max, and the smallest value is the absolute min. Can't be any easier. It's just wordy. Anyway, have fun thinking about the absolute maxes and mins in your life and in your functions. I'll see you soon.